you stuck with us. Good for you. In this screencast, we take a look at Simpson's rule, which is a way to approximate values of definite integrals, and it was, well, Simpsons. So the whole idea with Simpson's rule, you got some function like this, and it's on some interval from A to B, and you're looking for an approximation of the integral from A to B of f of x dx. And how are we going to find this? Well, Simpson appealed to parabolas. So Simpson said, let's break this up into some number of intervals. And on every 3, so if you consider 3 cut points in a row representing 2 subintervals, you take this point, this point, this point, and you fit a parabola to those 3 points. You use what's called a parabolic splice. And then you come over to here and you say between this point, and this point, there is one parabola that goes through all 3 of those points. And then you keep doing that all the way across. And for reasons that are well beyond the scope of our course, knowing that there are parabolic splices within the scope of our course, knowing where this comes from beyond the scope of our course, the integral is approximately delta x over 3 times. We take the first x value and then 4 times the next and 2 times the next. And then it keeps going 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 1. 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 1. That's Simpson's rule. So it's a delta x over 3 instead of a delta x over 2. And it doesn't go 1, 2, 2, 2, 2, 2. It goes 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, 1. I will illustrate. Let's approximate the integral from 0 to pi of sine x dx with Simpson's rule with 4 subintervals. Simpson's rule with 4 subintervals. Well, here's the region in question. And 4 subintervals means that that's halfway, and that's halfway between those, and that's halfway between those. So there are 4 subintervals. Simpson's rule says that the integral is approximately delta x over 3 times a y value, 4 times a y value, 2 times a y value, 4 times a y value, a y value. What's delta x? It's this distance. So this turns out to be pi over 12 times 4 square roots of 2 plus 2. Is that good? Yes, that's really good. That's really, really good. So how good is Simpson's rule? How good is Simpson's rule? Well, let capital M be an upper bound on the absolute value of the 4th derivative of f of x on AB. Then the error by Simpson's rule is no bigger than that capital M times b minus a to the 5th over 180 n to the 4th. Totally not a formula worth memorizing. But notice the 180 is much bigger than the 12 from the trapezoidal rule, and the n to the 4th is much bigger than the n squared from the trapezoidal rule. B minus a to the 5th is also bigger than b minus a cubed from the trapezoidal rule. So taking it back over here, The error coming from Simpson's rule is no bigger than, that m is still 1, right? Fourth derivative is sine x. Sine x is never bigger than 1 times b minus a to the fifth over 180 n to the fourth. Well, this is approximately 0.00664. So this number is no further away than that from the actual answer. And that's really good. That's 2 decimal places of accuracy for sure. So again, what's the moral of the story? By making the number of subintervals bigger, we make the error smaller, which means we get a better approximation. That's important. And by making the intervals smaller, we can make the error smaller. So there you go. Hope this is helpful to you, and hope that you're able to crank out some numerical approximations in the discussion.